Hello, everyone. Welcome to Islander EI, and welcome to the most secure browser, Pwning Chrome in 2016 to 2019, with Gunming Liu. Before we begin, I've got a few notes. If you'll stop by the business hall located in Mandalay Bay, Oceanside and Shoreline, level 2, that's where the welcome reception will be at 5:30, and it's also where the Black Hat Arsenal is being hosted. The Pwning Awards tonight are in Lagoon JKL at 18:30. Lunch is in Bayside AB from 12:05 to 1:30. If you'd do me a favor and do what they said a second ago and silence your phones for me, that would be great. And other than that, let's get a great round of applause and get this talk started.
Hello, everyone. This is Gunming from Tencent King Lab to give you the talk, the most secure browser, Pwning Chrome from 2016 to 2019. You have probably noticed that there should be two speakers here, but only one. This is because my partner, Zheng, cannot come because of the visa. So, but don't worry, I will have him share his part. And we are both security researchers at Tencent King Lab. And we have participated in Pwning for several times and have won 3 months of points. And our presentation is in 4 parts. Let's go to the first part, the SET set. Now let's type main set in the terminal. Set is short for semantic equivalent transform. Zheng came up with the idea in the late 2016 and added it into his father. It's easy to use. We feed it with JavaScript files, and it gives us new JavaScript files. Before we go into details of set, let's see the state of the art. Nowadays, when we talk about browser exploitation, the JavaScript engine has been a more and more attractive target. More and more people began their research in this field and publicized their findings, such as papers and tools. This year only, there are Fazili and Code Alchemist. Both are amazing tools. So what is fuzzer? There are many answers. Here are 2 of them. On the one hand, fuzzer is an I/O process. It consumes the input and gives output. On the other hand, fuzzer can be viewed as a searching process. We are hunting for crashes, aren't we? Different views bring different questions. One of the most important questions is that why there is no mutation-based fuzzer looks like this. It receives a JavaScript file and transforms it into the abstract syntax tree. Then it does mutation on the AST, and finally it transforms the mutated AST into JS again. Of course, it will also implement the built-ins, including the built-ins objects and built-in methods. It chases the creation of the scopes, the records, the variable, and the type information. If a variable is a function, we are also interested in its signature. When it comes to mutation, there are different strategies. Crossover, like the splice phase in the AFL. Also, it can do add, delete, replace, and the other modifications. Back to the question, why there is no paper or tools like this? My answer is that the idea is so instinctive that nobody thinks it deserves to mention in public, like what I am doing now. But actually, it is very effective. And this is the first bug he found in V8, which is exploitable. It's a typical redefinition bug. It redefines its concat spreadable symbol and breaks up the assumption of V8. He found the bug, but it doesn't belong to him. Someone else reported to Google. And you may notice the question mark in the title, but actually the bug is very good to exploit. The total exploit, which pops up a calculator, is no more than 30 lines. If you are interested in the garbage collection of V8, this bug is a good startup. And so bug collision is the most annoying. It also reminds me of another bug. That is, we used it to Pwning Edge browser in Pwning 2016. It's also a redefinition bug. We found it by fuzzing, but the bug is too easy to audit. And that's why we were so nervous when Loki tried to Pwning Edge before us. This bad experience tries to think how to avoid bug collision. Looking at the piece of code, I am lost in thought. What should we expect from this seed? A POC like this or this? My answer is no. Imagine that our seed is here and a POC is here. but I don't expect that I can find it because the searching space is too large. We must be a lucky, oh, sorry. We must be a lucky dog if we find it. And how about this? Looks good, and there are still 2 stars in the searching space. It can be smaller, and there are even no stars. But don't worry, we should believe that there are many hidden stars in the picture. And this is what SET does. In the picture, they are so close to each other that you cannot tell from them. SET tries to find the POC very similar to the seed. And we found CVE 2016-5198 from this seed. We used it to pwn Chrome in Mobile Pwning 2016. Let's see what SET did with the seed. It wrapped the assignment statement with the function declaration. Of course, we must call it at the original position because JavaScript doesn't implement dynamic scope. And we use check catch in case it introduces new arrows here. In fact, the check catch is very important. It stopped the compiler to inline the new small function. And we inserted an empty loop. In general, empty loop can speed up the optimization. And we repeated the check catch statement. Because V8 changed something about handling the recursion, we rewrote the POC in the form of for loop. And that is my job. That's how SET mutates a seed. The new files are very similar to the original seed, but they have different CFG and DFG, and we expect compiler will generate different JIT codes. The list is far from being complete, but it shows some very useful transformations. We also label each with stars. More stars means more effective, at least in our fuzzer. Loopanize wraps statements with loop structures such as for and while. We have seen functionize empty loop and repeat in our last example. SET also inserts some statements which triggers garbage collection. Conditionize includes jump and compare, such as if statements. Take functionize as an example. What can we do with this assignment statement? There are at least 7 kinds of transformations. Besides, each function can be both global or local, so there must be more transformations we can take. It's like the isomers. They have the same elements but different structures, and their characteristics are totally different. And here's a story from him in the first-person narrative perspective. I ever disabled all the other faces, but only enabled the set face. I ran the fuzzer 3 nights on my poor Surface Pro. And every morning I opened the door and took a peep at the screen. And in the 3rd day, I found a crash detection. At that moment, I was quite confident that the crash must be good and likely to be exploitable. All the transformations of SET also have the smart version when we know the context. For example, if there is a number or an array, we can use the number or the length of the array as the loop times in the for loop statement. We just uncomment the lines so that SET can co-work with all other phases, and SET then can take the advantage of the information collected in the early phase. There are some results from our fuzzers. You may notice that the keyword for is everywhere, and that's what we expect from SET. The last one is the bug we used in March this year, and we found it in early 2018. We ever found a bug which had existed for more than 4 years, and we used it to pwn Safari in 2017. The difference between the seed and the POC is only a for loop. That is amazing. And as everyone knows, exploitation is another key point in pwning contest. So in this section, we will share some interesting cases and our exploitation technique. Here is the first case we want to share. This is the POC of CVE 2017-5053, which is used in Pwning 2017. This is a very typical redefinition bug and gives us the out-of-bounds access capability. However, not like the other arrays functions, index of and includes can only return a Boolean value or an integer. So there is no out-of-bounds write, and we cannot get a pointer from this out-of-bounds read. It is worth mentioning that In May this year, Stephen from Google posted a technical article on Project Zero's blog about exploiting a similar bug in JIT. In the blog, Stephen introduced a way for leaking the array buffer backing store suggests, so I'm not going to talk more about it. But there's a difference between two bugs. In this redefinition bug, we can set the array's length to 0, and its element array will point to the empty fixed array, which means we can leak the pointers located in the pre-allocated old space. In 2017, there is a code space pointer in the old space, so we can leak it. After we got the address of the code space, we can put our share code, which is constructed by double value in JIT on the code space. This is also known as JIT spree. So the only thing we need is to control the PC register to jump to our share code. Also similar to Stephen's approach, we use the string compare for next step. There are several string types in V8. For external string, it holds a pointer which points to another string in other components. For example, the WTF string in Blink. And the string in other components always use virtual function call for the comparison during the index of search. So if we can fake an external string and control the virtual table, we will have the PC control. And here is the layout of the fixed external string. The type information of the string is stored in the tag field. So we need to carefully construct the map. And the external pointer points to the fixed virtual table, while the comparison function is at the 5th index of the virtual table. And after carefully constructing the string, we put the address of the fixed external string on V8 heap and use the out-of-bounds compare to trigger the virtual function call and jump to our share code. So that is the first case we want to share. Before the next case, let's go back to mobile Pwning 2016. And this is my first exploit on JavaScript. There are two optimized functions, and in check function, the optimized code would write the number directly to the property in native assembly. However, we have already reset the global variable m in CTOR function, so it will lead to out-of-bounds write on empty fixed array. In this bug, we proved that the out-of-bounds access on empty fixed array can lead to arbitrary address read and write. And if you are interested in the exploitation, you can find my talk on Kansec West 2017. Here, I really want to recommend the properties for exploitation. And V9 is a challenge in C3 CTF, which is produced by Cello. It's not a difficult challenge, but I found that almost all public exploits take advantage of confusion of the double array and the elements array, except for Cello himself. Cello took advantage of the mismatch between descriptor array and the properties. And I think it is more convenient because it doesn't need to fake object. This approach depends on the wrong information in descriptor array, which is stored in map. So the map of the object must stay valid, but sometimes the situation is more difficult. This is one of my bugs which can achieve code execution in V8. In one of the old versions of V8, this bug writes undefined to map and the property field, so it will destroy the map of the object. And in such case, we cannot use the traditional ways to exploit it. This is the standby bug for Pwning 2017. This is also a low-quality bug like the previous one. Because of the time, I'm not going to introduce the details of this bug. And in summary, this bug has the out-of-bounds pop on the newly allocated hash table, and the offset of pop operation depends on the high for bytes of the pointer, which obviously cannot be predicted or controlled. So it is more like an uncontrollable use after free rather than the out-of-bounds read. To exploit these low-quality bugs, we put forward the JIT fragment in mobile Pwning 2016. Let's take a look at the assembly code. First, it takes out the hard coding address from the global variable s. And then it takes out the property array of the global object. Next, it directly writes the number to the first property of the property array. And finally, it returns undefined. we can find that there is no map check in this optimizer function. In general, In general, there's always no map check on the global variable. But if you modify this global variable, V8 will notify the optimizer function to de-optimize. But think about this question. What if we modify the global object by mistake? Or in other words, if we can use memory corruption to modify the global object, will the function bail out? The answer is no. So we put forward a template for of this approach. First, we prepare the global object and its properties, and then we prepare the check function to write on its properties and optimize it. After that, we trigger our bug to corrupt the global object S. And finally, we trigger the optimizer function again and write directly on the corrupted object. And take the second bug as an example. As I said just now, the out-of-bounds read always access on the freed memory. So we first prepare so many set objects live on V8 heap. Because the out-of-bounds read is uncontrollable, so we have to trigger the bug looply. And we use instance of to check the return pointer. Instance of is very safe, which can avoid segmentation fault during the loop. If we found a pointer which points to a set object, we save it in the global variable. And then we prepare the properties and optimize the function on the global variable. And actually, the set object is released. So after we spray so many null objects, it will be overwritten by null. And finally, we trigger the optimize function again. It will directly write the prepared value to null. And the following step is as the same as the out-of-bounds access on empty fixed array. This is just an example that takes advantages of the elimination in optimizer function to exploit low-quality bugs. I believe you can find more of it. And now let's go to the third part, the Chrome sandbox bypass. Since 2016, we have successfully pawned Chrome 3 times in different ways. The first time is mobile pawn in 2016. We used a logical bug in renderer to start the web view in privileged app. And then we attacked the web view again to obtain the code execution with high privilege. And in recent years, kernel is a very popular attack surface in browser sandbox bypass. However, due to Win3 2K lockdown, it is very difficult to attack kernel inside the Chrome sandbox. In 2017, we found that CLFS is a good attack surface which can be accessed in Chrome. And we successfully got system at that time. Unfortunately, this attack surface is killed in Redstone 3 by the sandbox token. The third time is March this year. We used the use of the free bug in IndexedDB to bypass Chrome sandbox, and this is the main character in this section. IPC attack is very popular this year. At the end of last year, Ned Williamson first publicly shared the attack against IPC. After that, Mark Brand from Project Zero also posted a blog about IPC bugs. We have learned a lot from their great sharings, so I want to thank them here. Before we go deep into the bug, we need to know more about IndexedDB. Here's the example of using IndexedDB in JavaScript. First, we can open a database with a given DB name and version. The function will return a request. And then we can bind some callbacks to the request. If the database is successfully opened, it will be sent back through the upgrade needed callback, and we can obtain the database object from the event argument. After that, we can create object store and index on the database. We can also use delete database to delete the IndexedDB database. Because we already have code execution in renderer, we can directly call IPC functions in native way. There are 3 IPC interfaces related to IndexedDB, and we will focus on the first one, which is related to our vulnerability. There are 6 IPC functions defined in IDB factory interface. We can easily construct our POC in IPC calls. Firstly, we call open on DB1, which will first initialize the database in the browser side. After the database is completely opened, we call next 3 IPC functions inside the callback of the first open. It should be noted that not like the first call, the last three operations must be performed together, and these operations are all asynchronous, so each operation cannot be completely executed. IDB factory is responsible for managing IndexedDB database, and there is a database map in IndexedDB factory which holds a raw pointer to IndexedDB database. Notice that the raw pointer is very dangerous in C++ because there's no any protection on a raw pointer. After the delete database with the false close flag, the raw pointer in the database map should be removed. However, there is an active open request when we try to force close the database. The open request will be performed during the force close, and it will create a new connection. We can take a look at the code. If we call delete with the force close flag, it will force close it immediately. And during the force close, the connections to the database are iterated and force closed. However, if there is a pending connection waiting to open, the request would execute once all the other connections were destroyed and create a new connection. As a result, the connections and the active request is not empty, so the two debug checks failed. More seriously, it will prevent the database being removed from the database map. And finally, we use abort transactions for database to remove all transactions. It will release the database since all references to the database are cleared. So the raw pointer in database map points to a freed memory. Now we have a raw pointer that has been released. Then we need to find out where it is being used. After some auditing, we understood more about open and delete database. These two functions are very similar. Take open as an example. When we start opening a database, it will first search in database map according to the DB name and its origin. If found, it will directly return the database pointer in the database map to perform the following operations. In other words, we can do open and delete operation on a freed database. To exploit Chrome on Windows, we need to learn some basic knowledge before we start writing our exploit. Firstly, there is no control flow guard in Chrome process on Windows. Secondly, the library address in every process on Windows are same, so we can obtain the library address from the compromised renderer process. Thirdly, there are many virtual function calls in C++ implementation, so it is easy to control PC register. The only thing we need is a heap address to put our rob chain on, so we need to leak a heap address first. We also noticed that if we successfully open a database, it will return some information such as IDB name and object store names. And they are both object of base string structure. And we all know that string is very good for info leak. So until now, everything looks fine. Let's take a look at the code. The connection, open connection and the delete database are very similar. When we call open or delete database, they won't do it immediately. Instead, they first create a new request, and then they pass the new request to append request function. In append request, the newly created connection request is pushed to pending requests, which is a circular queue. And if there is no active request, it will process the request queue immediately. In process request queue, it takes out the first request of the queue and then call the virtual function perform on the request. In the perform function, we can see that if we can successfully open the database, it will send back a connection and the DB's metadata via unsuccess callback. Besides, metadata is a member object of structure type IndexedDB database metadata, which includes a base string. Obviously, we can easily control the string since info leak is not difficult to us. And after carefully constructing the fake IndexedDB database, I successfully reached the unsuccess callback. But then I got the segmentation fault. After some debugging, I found out the reason. This is because there is also an STD map in metadata, which is implemented as the red-black tree in libc++. During the callback construction, it has to copy construct the IndexedDB database metadata structure, which needs to iterate the STD map. The end of the RB tree traversal will point to the object itself and represent the end. This means we have to know the address of metadata itself to end the traversal, but we don't know anything about the heap address. So we have no choice but to find other ways to continue our exploitation. Let's go back to append request. The active request is a member of IndexedDB database, which is fully controlled. And if it is non-zero, the function will return directly so that we can avoid the segmentation fault in process request queue. Now let's stop the boring code analysis and to see the results in the debugger. First, we construct our persuade exploit. We prepared an array buffer in size hex 148, which is in the same size class as the IndexedDB database. And we set the active request to 101. Then we use blob to do heap spree. It is worth mentioning that blob is the most popular object for spree in Chrome. And finally, we call delete database. Need to add one more thing. Here, delete database is the same as IndexedDB open, since we won't process the request queue. In debugger, we set a breakpoint at the delete database function. And notice that the RDI register represents the first parameter in Linux, which points to our magic number, 1111. And this means we have already controlled the IndexedDB database. And here's the memory of IndexedDB database before the deletion. And then we continued the execution and received a gift. We surprisingly find that after the delete database, there is a heap pointer on the object, and everything goes well. So what is the heap pointer here? Let's go back to append request again. Remember that appending requests is a member of base queue structure. If we leave everything zero, it will automatically init during the first push operation. It first allocates a container buffer for storing its elements, and then store the container pointer to itself. So we must thank base queue for this gift. And remember that the object is not only an IndexedDB database, but also a blob. So we can easily read the heap pointer from the blob. Now we got the heap address. The following step is almost copied from Ned and Nicholas B's exploit. So thank them again, and I will skip this part quickly. There is a virtual call in doDelete, and we can easily control the virtual table. The exploit chain is shown in this diagram. First, we trigger the bug to release the IndexedDB database. Later, we spray blobs to fill the hole. After that, we call delete database and leak the heap pointer from the blob. And next, we free the leaked blob and refill the hole with new content. Then we spray so many page heaps, which includes our ROP chain. And finally, we trigger the virtual function call and start ROP. Actually, there are some obstacles in the exploitation. For example, Chrome uses tcmalloc for its heap management. And in our bug, the IndexedDB operation is in the IDB thread, while the blob allocation is in the IO thread. And actually, it is very difficult to fill the hole from a different thread cache. Unfortunately, because of the time, I cannot share more about the details of tcmalloc. And if you are interested, we can discuss after the talk. Since the exploit on Windows is not fresh and not very difficult, so we prepared more for my audience. In addition to V8 and the IndexedDB vulnerabilities, we also reported 3 Chrome OS bugs for Pwning. So we needed to exploit Chrome sandbox on Chrome OS, which is much more difficult challenge. The first thing I need to say is that Chrome on Chrome OS is very similar to it on Linux, because Chrome OS is actually a Linux kernel-based operating system. So the following exploit and the demo is actually on Linux, but the approach is same on Chrome OS. To the best of our knowledge, it might be the first public exploit after the CFI is deployed on Chrome. So let's check the difference. The biggest difficulty on Chrome OS and Linux is the clone control flow integrity, which protects all indirect calls, so we cannot attack the virtual function anymore. Besides, the binary and the library address in main process is different from the renderer process, so we have no binary and the library address this time. In history, we cannot find any bypass methods on clone control flow integrity except stack-based corruption. However, stack-based attack is also very difficult in Chrome. First, we need to know the stack address and the binary address, and even worse, Chrome uses thread pool for handling IPC messages, so we might attack thread stack, which is a little bit random. Besides, it also requires high-demand arbitrary address write capabilities. In summary, this seems to be an impossible task for me. But don't forget that Chrome is a huge system. We can easily tamper with lots of logic through memory corruption, not only the traditional PC control. So don't be trapped by rules, just free your imagination. There are more than 100 flags in Chrome, and some of them are interesting. When I was reading the Chrome's documentation, I found that the renderer command prefix might be the one I needed. To dig more about it, let's check how a renderer process starts. Each rendering process corresponds to a render process host in browser side, responsible for the management of the process. During the initialization, it first gets the value of renderer command prefix from browser command line. And then it prepends the renderer command prefix value to the command line variable. Finally, it uses the variable to launch the child process. This means if we are able to control the value of renderer command prefix, we will control the command line of the child process and launch anything we want. And here's the example. Start Chrome with the renderer command prefix flag. The value will be prepended to child process command line. As we said, render command prefix is stored in browser command line. So the next question is that, what is the browser command line? After a little research, we found that it is from a static function which returns a global pointer, and all command lines are saved in the switches of the global variable. So for command line injection, we only need two things. The first one is a binary address because the global pointer is located in the BSS segment. And secondly, we need an 8 bytes write to hijack the pointer. The mission seems much easier, but until now, we only have a heap address, no more leak and no write. So I want more. Luckily, BaseQ is more valuable than we expected. Base namespace implements some basic structures. Some of them are very similar to std, but a little bit different. BaseQ is an example. It is like stdq, but use the circular deque instead of deque for its container. BaseQ is a 4-pointer size structure. The layout is as follows. The first field of BaseQ is a container pointer, which points to the elements array. And the second field is the size of the container array. The third field is the front index of the queue. And the last field is the rear index of the queue. Remember that we can append requests for any times with no side effect. So we can play with the queue freely. And there are two different situations. If the queue is not full, it will push the new request to the container. Since we can fully control the container pointer, we can write the new request pointer to any address. And if the size is equal to the length, it will expand the storage automatically. In detail, it will increase the storage by a quarter, which needs to reallocate the buffer. It first allocates a new buffer, then move the previous memory to the new buffer. Finally, it frees the previous buffer pointer. Similarly, the previous pointer is controllable, so we got the arbitrary adjust free. But be careful of the memory move. It will clear the memory according to the given size. So before free, we have to guarantee that the buffer size is larger than the queue size. And we have to thank base queue again. Then let's see how to take advantage of the arbitrary free. Every time we call delete database, the length of the pending requests increases by 1. So here we first increase the length of the queue to 34. Here is the memory of pending requests after the first deletion. And after we delete database 3rd times, the length of the queue goes to 3. And the 4th deletion will trigger realloc. The size increases by a quarter and the previous buffer is cleared. After 34 deletions, the size of the queue goes to 42, which is hex 150 bytes. Remember that the size of blob and the IndexedDB database are both 148, so they are all in the same size class in tcmalloc, which actually consume 160 bytes in memory. Since we have already spread thousands of blobs in the same size, the container buffer will have high probability of being surrounded by the blobs. Next, we read the address of the container buffer from the blob. The variable leak address should be the value of container pointer. And then we subtract the leak address from the size of the structure. And this is very important. As I said, the container is surrounded by the blobs, so the new pointer is very likely to point to a blob. So here's a diagram. The leak address points to a blob that we spread. Then we use the arbitrary free to release the leak address. And the blob is freed. And then we immediately open a new database with a different name. Thanks to thread cache, the newly created database can reuse the space just released very stably. So now there is a database pointing to the same place as the blob. The handles of the blob in both sides are still valid, so we can also use the blob to read the content of the new database. From the vtable of IndexedDB database, we got the binary address. The last remaining problem is the 8 bytes write. We can now fully leak and control the IndexedDB database, so we can try more IPC calls in IDB database interface. According to the IPC name, we choose two candidates, rename object store and rename index. Remember that object stores are stored in an STD map, which is a member of metadata, while indexes are stored in an STD map, which is a member of object store. Just as their name imply, the two IPC calls can modify the name of object store and index. Let's take a look at the rename object store first. Before renaming, it will check if the current name is the same as the one it saved previously, and I found it is a little bit difficult to bypass this check, so I turn to the next one. There are also many checks on rename index, but fortunately, they are not very difficult to bypass. Besides, we can find the comment is interesting. It is a to-do comment to add the same check as the rename object store. Eventually, we can modify the name. At first, I thought I could do arbitrary address write through the strings character array, but I found out that rename was done by std move, which would cause the original character array to be freed and then replaced with a new one. Let's take a look at base string. There are two different forms of string. If the string length is greater than 24 bytes, it will use an external buffer to store its data. And std move will free the external buffer and replace it by a new one. Well, if the string length is less than 24 bytes, it will inline the data. And in this situation, even with std_move, it will write down the controlled data to the original place. Remember that we only need 8 bytes write, so it is enough for us to control the pointer of the command line. Let's see the diagram of the objects. Notice that everything in the graph is controlled by us, and we can modify the index name through IPC. Because everything is in control, we can set the index metadata to the address of a global command line pointer, which is in BSS segment. At the beginning, the pointer points to the original command line, which we cannot control. And then we use rename index to change the pointer and point to our fixed command line object. So now we can control the command line of the browser. And here is the version in JavaScript. And surprisingly, I found I was able to put everything in one blob. Actually, there are more obstacles and difficulties during the exploitation, but because of the time, I cannot share them all. So at the end of our talk, let's see the demo. Here's the official build of Chrome, and then we visit our website. The first part is V8 exploit, and it will be very quick. And the V8 exploit will patch the renderer process so that we can call the IPC functions directly. And remember that we have to spray thousands of blobs, so it might take some time. And in the last stage, we open a new renderer process by the frim in browser. And let's check the task list. And we can see that we successfully prepend our command to the child process of Chrome. And it will download the bash script from our server and execute it. So that is all for my presentation, and thank you for your attention.